Okay, until the PDF loads, talk about some vocabulary. If I were to use evenly spaced nodes, we call that Newton-Cotes quadrature. You knew that. If I use Chebyshev nodes of the first kind in a node as the nodes in a quadrature rule that's based on exactly integrating the resulting Lagrange interpolating polynomial, this is called, new word, Fejer quadrature. Okay, named after a mathematician back in the 30s, 1930s, named Fejer. And then lastly, if I were to use those nodes of the second kind, this is what we call Clenshaw-Curtis quadrature. So named after two mathematicians from like the 60s. And they came up with Clenshaw-Curtis quadrature. Because this topic of like numerically integrating functions well didn't really appear in a great deal of excitement and detail until after computers were invented. Like, when did people have easy access to computers? Not until really like the 70s, you know. So you start to see people getting more excited about numerical analysis around the 60s and 70s. Okay. Reader went over that table. Whenever you have now quadrature rules that are supposed to approximate integrals and you're basing them off of these interpolating polynomials that are based on these nodes, what we're going to find is because Newton-Cotes, or because the evenly spaced nodes are bad at handling Runge's phenomenon, they're not actually guaranteed. Newton-Cotes quadrature rules are not guaranteed to actually converge. And when I say converge, man, I really wish I had a PDF to draw on.
I mean, you could draw on that.
I know, I just don't want to mess up my my Word document. Because I don't want to. Man, okay. I don't want to mess up my Word document, but I wish I could write this out. When I say it's not guaranteed to converge, I'm talking about, what if I want to keep increasing my number of nodes, right? I start off with 3 nodes, and then I make it 5 nodes, and then I make it 9 nodes, and then I make it 17 nodes, then 33 nodes, right? I keep growing the number of nodes. Newton-Cotes will make a sequence of approximations that are not actually guaranteed to converge to the true value of the integral. So if you were using a Newton-Cotes quadrature rule, what you actually want to do is don't adjust the number of nodes. Instead, you would use a composite rule, right? You would just subdivide your interval into smaller sub-intervals and then apply the rule on each one, right? Because even if you just have like the trapezoid rule, or you just have Simpson's rule, you know that using the composite Simpson's rule, that will converge to the true value of the integral as you increase the number of subintervals. So composite rules make sense for Newton-Cotes. But Fejer quadrature and Clenshaw-Curtis quadrature, those rules are guaranteed to converge. So as I increase the number of nodes, then I don't have to worry about doing a composite rule. I'll just keep increasing the number of nodes I use in my quadrature rule, and that's guaranteed to converge to the true value of the integral. So this is it. If you were wondering, how do we define a Fejer quadrature? How do we define a Clenshaw-Curtis quadrature? All you really need to know for a quadrature rule is what are the weights and what are the nodes. F is the function we're trying to integrate. So we just need to figure out the weights and the nodes. The nodes, I already showed you those formulas, come from geometrically trying to evenly space points around a circle. And so that's where the cosine comes from here. The weights, just like any other quadrature rule, are going to come from integrating the Lagrange basis polynomial associated with the node from -1 to 1. And we are not going to do that, so you don't have to worry about this. You don't even have to memorize these formulas for the weights. But when you do that, when you do integrate the Lagrange-Massus polynomial, this is what you get as a formula for the weights. And it's a big, ugly formula, right? There's a lot of steps involved in calculating this. There's a sum. There's this symbol, which means round down. If you see like square brackets that are missing the top. Man, who wrote this on the board? If I have the number like 6.7, but I write these square brackets like that, that's telling me to round down to the nearest integer. So that would be 6. It's used here because I've got k divided by 2. So if k is an odd number and I divide by 2, I'll get like 4.5. And so you round down the 4.5 to a 4. But again, on a test, I will give you these formulas. So I need you to know how to use the formula, but you don't have to memorize this, right? That would be crazy. I'm not going to make you derive the weight formulas. I'm just not going to make you memorize them. I just need you to be able to use this in quadrature rule. And another thing that you might notice if you're really paying attention here is that the whole thing is only defined from x equals -1 to x equals 1. Right? When I was placing those nodes, I was using a unit circle. So what if I have a different integral with different bounds? What if I have an integral from lower bound 5 to upper bound 8? You know? Then we're going to use what's called a change of interval. This is a way of taking our function and sliding it to be centered around 0 and then scaling it horizontally so that it has lower bound -1, upper bound 1. What we're doing is we are replacing x with a plus b over 2 plus b minus a over 2 times x. Notice what happens if x is equal to a, right? That's a. No, sorry. I take it back. What if x is at my lower bound? What if x is -1 here? Then that's -1 times b minus a over 2. So in other words, that's a minus b over 2 plus a plus b over 2, and you get a, right? Plug in x equals -1, and then suddenly you're taking f of a. Also, plug in x equals +1 here, and then add these together. And then the a's cancel, and you get b over 2 plus b over 2. So you're taking f of b at your upper bound. So you're getting all of the right values of f between a and b whenever I do this. Plus, whenever I multiply by b minus a over 2, that's kind of like the constant that comes out of the u substitution. What I mean is, like, I guess I'll just draw on this, like, see how this goes. If I say u equals a plus b over 2 plus b minus a over 2 x, du is equal to b minus a over 2 dx. And so then I get the integral of f u. I might have done this backwards, right? Because that would be this du. The lower bound would be what I get if I plug in -1, which would be a, and the upper bound is what I get if I plug in 1, which is b. Interesting. Oh yeah, so then I would get this. I would get this on my left side of the equation. And to move it back over to the right side of the equation, I don't multiply both sides by 2 over ba. I divide both sides by 2 over ba. Let me check on the PDF and see if it's available yet. What's really funny is that I never have these issues in Calculus 3. It's only numerical analysis. Somebody in here is like a bad luck charm.
Can't be me, Connor, right?
Mm-hmm. Surely can't be computer science majors. We
Well,
never flunked
so
it.
it never happens when Tony's here, so it's Tony's fault.
Like the thing when the TV kept turning off? That only happened in numerical. It never happened in Cal 3. But see, there it is. Kevin, look. That's the file I want to open. Why does it show up there and not here? It doesn't matter how many times I hit refresh, I can't see it.
If you click on the blue cloud that's in the bottom right of the screen, OneDrive one. If you click on the gear in the top and then
maybe pause syncing, resume syncing. There we go. Yeah, Kevin fixed it. Okay.
That was so good. Wow.
Kevin caused it, but Kevin fixed it too, so. Okay. Okay, so this is what I'm trying to explain. Look on the left side, or on the right side. I'll do this one more time. I've got b minus a over 2 times the integral from -1 to 1 of f of a plus b over 2 plus b minus a over 2x dx. And I'm saying, let me use a u substitution to solve this integral. So my u substitution is going to be a plus b over 2 plus b minus a over 2x. So the du is going to be b minus a over 2 dx. Right? So I'm going to replace the dx with 2 over b minus a du. That's what I'm going to replace that with, and replace that with. And so after u substitution, this is going to be b minus a divided by 2 times the integral from my new lower bound is what I get if I plug in -1 for x here, which gives me a. And my new upper bound is what I get if I plug in +1 for x over here, and that gives me b. And this would be f of u, and then dx gets replaced with 2 divided by b minus a du. Okay, now this, the b minus a over 2, and this 2 over b minus a cancel each other out, and I get the integral from a to b of f of u du. And it doesn't matter what symbol I'm using. I can use a u, or I could use an x. But this is how it's related to the integral on the left side of this equation. And so you can verify you've got the right change of interval, and it's still going to calculate the same integral for me. So if I want to use a Clenshaw-Curtis quadrature to approximate the generic integral that goes from a to b, then this is what I'm going to do. I'm going to apply my quadrature to this integral on the right, because I know where the nodes are between -1 and 1, and I know how to calculate the weights for those nodes, because there's a formula for it. And then after I do that, where these xj are the plain old nodes, right, on the interval from -1 to 1, and these are those weights using the formula. I just have to multiply by b minus a over 2 to get the true value of my integral. So even though this scheme of Fejer quadrature, Clenshaw-Curtis quadrature only is defined for -1 to 1, we can still integrate any integral we want over any domain we want just by using that change of integral. So let's talk about degree of exactness. It's really boring. We already discussed why in our lecture about Newton-Cotes quadrature, how the odd terms cancel in the quadrature rules and the odd terms cancel in the true integral as well, because of the whole even-odd function thing. We even went on a rant about that in Calculus 3 today, about how odd functions, right? It's the odd functions that cancel each other out when you integrate. So it's the same. There's nothing new. There's nothing more special about Fejer or Clenshaw-Curtis quadrature that changes that. We still get to appreciate the same degree of exactness as we do with Newton-Cotes quadrature. I kind of alluded to this earlier, but Fejer published in 1930. He was working alone, and he had a really long title for his paper. In 1960, so 30 years later, Clenshaw and Curtis co-authored their paper, and I thought this was a funny title, A Method for Numerical Integration on an Automatic Computer. Because remember, computers are kind of new, so you had to distinguish between an automatic computer and a human computer, because computer used to be a job title. You could go and sign up to work somewhere as a computer, and you would just sit down all day and do numeric calculations by hand or with a slide rule. But that's what they called computers. So an automatic computer was an important distinction for the 1960s. Today, if you were to look at a program like MATLAB or the NumPy library in Python or anything like that, modern software will never use Fejer quadrature because the nodes don't nest, right? Ideally, we want a scheme where we can choose a small number of nodes and see what our error is, then choose a larger number of nodes, see what the estimated relative error is. If it's too much, then choose an even larger number of nodes, see what the estimated relative error is, and then if it's still above our tolerance, we choose an even larger number of nodes, and we, again, find the estimated relative error, and we keep doing this until it fits underneath how much error we can tolerate. If you're using a scheme like Fejer quadrature, every single time I iterate, every single time I repeat the process and choose a larger number of nodes, now I'm calculating a fresh set of nodes that has a fresh set of weights. And beyond that, I have to calculate the value of my function at those nodes. And sometimes calculating the value of the function takes up a whole lot of flops, takes up a whole lot of computer resources. So we want rules that are nesting. And since Clenshaw-Curtis still performs almost as well as Fejer, and I can keep the same nodes and the same function evaluations and the same, not the same weights. I take it back, sorry, not the same weights. I can keep the same nodes and the same function evaluations, though, every time I increase the number of nodes, then that decreases the amount of computer resource I have to use when I use an adjusting scheme to achieve my desired level of accuracy. And for the same reason, we don't use composite rules. Because why would I ever choose to subdivide my interval into two intervals to increase accuracy if I could just double the number of nodes, right? It's the same amount of compute, but you're going to get better accuracy by doubling the number of nodes than you do if you just subdivide into two intervals. You're still evaluating the function at the same points. But composite rules, actually I take it back, composite rules wouldn't be nesting because we're not talking about evenly spaced nodes anymore. And so composite rules really don't apply outside of Newton-Cotes quadrature. Because here's my Clenshaw-Curtis nodes, which are a little bit more dense near the endpoints. And if I want to double the number of nodes, I have to just do 1, 2, 3, 4 more function calls But if I wanted to subdivide my interval, well, now I've got to choose 1, 2, 3, 4, 5, 6 new places to evaluate my function instead of 4, and then this is going to be worse. So you might as well just double the number of nodes. Another little table. I love tables for summarizing stuff. For all 3 of these quadrature rules, the node locations are easy to calculate. The weights are easy to calculate for Fejer and Clenshaw-Curtis. And yeah, I know the formulas are big and ugly, but there's still a formula. Remember with Newton-Cotes quadrature, there wasn't even a formula for the weights. You had to reintegrate the Lagrange basis polynomial from scratch if you ever wanted to calculate the weights. So that's what I would call not easy. Of course, we talked about nesting nodes. We talked about the degree of exactness. Oh yeah, I guess I really didn't finish. The last thing I was going to put in this lecture is just like an example of using one of these quadrature rules. And so maybe we should try that. Let's try an example function where we want to integrate, make this easy. Let's say we want to do this integral. And we want to use Clenshaw-Curtis with 5 nodes. So for one thing, I'm going to need to know the locations of those nodes. x0, x1, x2, x3, x4. And since this is Clenshaw-Curtis, I know that the endpoints are going to be nodes. And I know I've got an odd number of nodes, so the midpoint's going to be a node. I really just got to figure out where is x1 and x3. And then I will need to know what is the weight assigned to each one. And these nodes are placed symmetrically. And so I only have to calculate 3 of those 5 weights. The last 2 are going to be symmetric to the first 2. And then, of course, we're going to make my approximation by summing up what I get k is 4 here. So I'm going to make the sum from j equals 0 to 4 of wj f of xj. F, my function, is 1 over x squared plus 1. So let's figure out what is x1. And with Clenshaw-Curtis, our formula for the node location was cosine of, I believe, j divided by k plus 1 times pi. And so when j is equal to 1, this is going to be 1 divided by 5 pi. No, I don't think there's supposed to be a plus 1 there, is there? It's just supposed to be j over k. It's an important question. Because my nodes are supposed to be evenly spaced around this circle. Here's 0, 1, -1. And so if I've got 5 nodes, here's 1, 2, 3, and the fourth one's going to be like right here, or sorry, in the first and the third. Okay, so here's x0, here's x1, here's x2, here's x3 and x4. So when j is equal to 0, this should be cosine of 0, which is 1. When j is equal to 2, this should be 2 divided by 4, which is 1/2 pi, which is cosine of pi half, which is 0. Yeah, so there should just be a k in the denominator, which now is really making me second guess myself. Did I write down the right formula? For these nodes? Yes, I did. Okay, good. Good. I got scared for a second. Okay. So I've got cosine of 1/5 pi. And that's going to be 0.809 to 4 significant figures. And then because this is, again, symmetric, this is going to be negative 0.809.
Wouldn't it be 1/4? Because you changed it from.
Oh, you're right. Thank you. Which is square root 2 over 2. I guess it doesn't really matter how you number these. You know, on my picture, I numbered them 0, 1, 2, 3, 4 going counterclockwise because the cosine function kind of goes counterclockwise around the unit circle. Over here, I numbered them from left to right on the number line because that's another way I tend to think of things as like counting, reading from left to right.
So it's not wrong that your negative number is on the wrong side of the picture. For the picture, it makes sense.
It's fine, right?
That's
Are you cool with it?
Yeah.
I mean, in the end, what are we going to do? We're going to add them all up.
Well, you got negative.
It doesn't matter whether I add the negative one first or the positive one first. You know. We're still going to add them all up in the end. It's like my dad used to say, you know, I was like a little OCD kid. I wanted my macaroni and cheese to be on this side of my plate and my chicken to be on this side and my green beans to be on that side. And if the food touches, I'm like, Dad, quit making the green beans touch the mac and cheese. My dad said, you know, it's going to get mixed up in your stomach anyways. This is the same thing. It doesn't matter what order they're going to be in. I'm going to add them all up anyways. You won't be able to tell. Addition is commutative. So now the weights, right? We got to do the weights. And the weights is going to be the annoying part of this. And there's nothing hard about this. It's just a matter of, do you have the stamina to sit down and work this formula? So W0 is going to be Cj divided by K. Well, Cj says it's going to be 1 if j is equal to 0. Okay, perfect. So it's going to be 1. K is 4 times 1 minus the sum from m equals 1 to 4 divided by 2, which is 2 bm. It depends on what m is, I suppose. Times cosine of 2m theta j theta j is going to be 0 divided by 4m squared minus 1. So it's going to be 1/4 times 1 minus, I'm going to go ahead and evaluate this sum. Starting with m equals 1, by the way, k over 2 is 4 divided by 2, so if m is equal to 2, b is equal to 1, but it's not. We're going to do the m equals 1 first, so we're going to call this 2. Cosine of 0 is 1 divided by 4 minus 1 is 3. So 2/3. That's what I get from the sum when I choose m equals 1. Then let's choose m equals 2 and get that second term of this sum. And if that's 2, then bm is going to be 1. Then cosine of 0 is still 1 divided by 4 times 2 squared, which is 4 times 4, which is 16. 16 minus 1 is 15. And then there's some calculator work to be done. 1 minus 2/3 minus 1 over 15 divided by 4. 0.06667. And that's the first weight. There's two other weights we need to calculate, W1 and W2. And then after we calculate the W1 and W2, then we would have something here and something here, and then we would take my function evaluated at these 5 points, multiply those function evaluations times the weights, add them all up. So you can see why it would be more fun to do this on Python and just have Python crunch the numbers, right? It's pretty easy to code. Every time you have a sum, you just have to turn that into a for loop. I just don't want to do the rest of it because we're kind of running out of time.